start a little bit about technology. Because we at the moment don't know is everybody knows about GPR or not. So what is GPR? GPR is radar which emits electromagnetic impulses, usually down, straight down, and it digitizes reflected signals from surface and from subsurface anomalies. What are reflectors? Reflectors for electromagnetic waves. It is not just a metallic objects or pipe or something. It's a different mediums or items with different dielectrical permittivity. For example, a GPR can detect not only a metal pipe in soil, but it can also detect layers of different soils or soils with different humidity or water content, because such mediums will have a different dielectrical permittivity. When GPR receives reflected signal, it digitizes it, and standard result of GPR survey will be in a digital form, of course, but most standard representation of GPR data is so-called two-dimensional profile. So if GPR is traveling from left to right, like here on the picture, it can be not only an onboard GPR, it can be GPR on a card. First, what we will see reflection from the surface. It is that strong line. If antenna is elevated a little bit above the surface, usually we will see such reflection, and also we may see layers like here, reflection from the different layers of soil, and also we may see something like hyperbolas here. In that particular case, hyperbolas are pipes crossed in perpendicular direction. Such representation of the data is actually too technical, I can say, and usually after processing we can provide more understandable or better representation or interpretation GPR data. Even in two-dimensional profiles, we can mark interfaces or margins between different soil layers. Like here, it's a surface, and here is a margin between sandy soil and bedrock, yellow line, and we marked two gas pipes which are on tops of hyperbolas in that survey. We can provide, as a result of GPR data, horizontal slices at the same depth under the surface, and here in that representation we can see the same pipes actually, but from above. And we can generate 3D representation like here. It requires a bit of more work for the data interpretation and processing, but 3D representation, three-dimensional representation is also possible. And one more standard product of GPR surveys is thickness maps. In that particular case, it is thickness map of ice, in ice covering lake close to our office. So we can profile the ice, we can generate a colored picture of the ice thickness, or we can export XYZ file with the same thickness of the ice. It can be not only ice, of course, it can be, for example, thickness of the sand layer over bedrock, or something like that, or thickness of glacier. So here are four more or less standard products of GPR surveys. Standard products, I mean, in the form which can be provided to the customer of survey. GPR technology is not new, actually, and there are few standard methods how we can carry or how we can use GPR. Most standard method, I don't know, maybe 90%, maybe 99% of all GPR surveys are with GPR on a card, like on that photo. Why that method is most popular? Because majority of GPR applications actually are inside of cities, on the streets, on squares, to find underground utilities. It's the most popular GPR application. What that application means, quite confined spaces, not very big survey areas. Sometimes it's just a few square meters before new digging. And in such surveys, in such environment, card with GPR is most optimal variant to use GPR. Second, also very popular method, some GPR systems can be used in box or on a sled, and GPR can be dragged. Here is photo from Greenland. It's me. I'm dragging 500 megahertz system over glacier. Actually, I even don't remember why I didn't use a drone here. And that survey actually was pain. It was not very easy to walk over snow, but such option is also possible. Exactly in similar conditions. When we cannot use a card because bearing capacity, possibility to push the card over snow or over some, I don't know, bog, it may be actually not possible. In such cases, we can just pack GPR into the box or place it on a sled and drag it. Also, many GPR systems allow kind of manual survey. When you carry GPR antenna, GPR system in hand, like here. It is on Aero LF, low frequency system, and you can use it using provided handle. So you may start data recording and just walk with GPR. And last method, which becomes more and more popular, it's GPR mounted on the drone. But again, I think it's my opinion that most popular method to use GPR will be, of course, a card. But if you will compare, if you will consider drone-mounted GPR applications, why GPR on a drone can be optimal? First of all, if you need to survey large areas without obstacles and vegetation, or with very low vegetation. When it is hard or not safe to walk in survey area, for example, over the glacier. But drone-mounted GPRs will never substitute old existing methods, and it is very important to have universal GPRs which can be used on card, on drones, in hands. That's all I think about technology. Let's start the introduction and comparison of new GPR systems. From our history, we started to work with airborne GPRs in 2017. And 600 megahertz systems are new for our portfolio. They fill the gap between very high frequency systems and low frequency systems. So here on the left is MALÅ GeoDrone 600. And here orange box is MALÅ GeoDrone, radar systems Zontaira 600. 600 means central frequency of GPR, and actually it's a main parameter of GPR. It strictly defines practical maximum penetration into soils or into mediums, into ice, snow, and also it defines resolution of the radar. Both radar systems have the same central frequency. That means they should have similar parameters and similar or absolutely the same, I should say, absolutely the same applications, possible applications. Of course, main question regarding GPR. What data they deliver? Here are two screenshots of GPR data collected in the same way. I will try to show you video how the data sets were collected. It is MALÅ GeoDrone. That's the road close to our office, and we use exactly the same line as a kind of benchmarking line for all our GPR tests. Why we are flying over the road? Because at the left and right side from the road, here is mix of heavy and usually very wet soil. A mix under the road is more or less dry, and we have very interesting strata layers under the road. So we can compare data collected using different GPR systems. So what we got in result. One of data sets is collected using MALÅ GeoDrone, second data set collected Zontaira 600, and actually I forgot what data set is from what GPR system. I prepared that screenshots yesterday, and when I pasted both images on the slide, actually I forgot. And it is good because I don't want here to have a discussion what apples are greener, what is better, because they deliver, both GPR systems deliver exactly what we expect from 600 megahertz system. You can see that data is very, very similar, even in small details. There is, of course, some differences, and main source of differences is that we did tests in different time. For MALÅ GeoDrone, we collected data set in the middle of summer, as I remember, in July. For Zontaira 600, we collected data in the middle of September. So humidity or water content in the soil mix was different, bit different surface conditions. What we can see, the data is from both systems is very good, and it is very, very similar. So in terms of data, and in terms of penetration, resolution, both systems work as expected from 600 megahertz. Here are main technical parameters of both systems. Both GeoDrone and Zonterra 600 are single-channel GPRs with shielded antennas. Shielded antenna means that they emit most of the energy of electromagnetic waves straight down. They have the same central frequency. They have a bit different frequency range. Because GPR, what is the maybe main difference between ground penetrating radar and navigation radars? Navigation radars use very narrow frequency range to get very high resolution and to get very predictable results actually. For ground penetrating radars, it is common to have very high frequency range of antenna to achieve from one side deeper penetration for the lower part of spectrum and better resolution for higher part of spectrum for more shallow layers. So here is small difference. In theory, GeoDrone should have a bit deeper penetration. Zonterra should have a bit better resolution in shallow layer, but it is just in theory. We can see the data almost the same. Both systems use real-time sampling with a bit different marketing wording. MALÅ use wording MALÅ HDR technology. Radar systems use just real-time sampling with high hardware stacking. But technically, in terms of delivery data, and I suspect implementation is also the same or very similar. Both radars digitized the data using 32 bits. That means very high dynamic range of data. That means that radar can show very small differences in recorded signal. Data for MALÅ GeoDrone is recorded in a MALÅ proprietary format, but that format is supported by many processing software packages. Of course, MALÅ supplies own software. It is called MALÅ Vision. Very popular online system for the GPR data processing called Geolytics also supports MALÅ. And I found that Prism 2 software from radar system, manufacturer of Zonterra, also supports MALÅ data files. Very interesting. Data from Zonterra is logged in most standard format called SIGY, and it is supported virtually by any software for GPR data processing. Size is a bit different. MALÅ GeoDrone is more slim, but it more longer. And main difference in the formal parameters, it's a weight. MALÅ has weight 2.7 kilograms. Zonterra has weight 1.7 kilogram. Difference is 1 kilogram. It can be quite important factor when you select radar or when you plan surveys, because 1 kilogram difference means approximately 10 minutes of light time difference for DJI M350, for example. But that will not be so important for DJI M400, for example. So full specs you can find by links. You all will receive a copy of presentation. So we saw that radars deliver very similar or practically the same data, but where is the real difference between systems? Not only weight and not only color and shape. I should say that molded plastic casing of MALÅ GeoDrone is very good. Very good from practical point of view. It better protects radar in case of hard landing, crashes, or just not very accurate handling or transportation. But it is on the cost of weight, of course. As I said, difference is 1 kilogram. MALÅ GeoDrone is a kind of self-contained sensor. It has internal data recorder, it has internal battery with optional with connector for optional external power, and it has internal GNSS receiver with antenna connector. So MALÅ GeoDrone can be used practically on any drone which can carry 2.7 kilograms and can follow terrain using some altimeter. It is very important because GPRs with so high frequency usually absolutely useless without possibility to have exact low altitude over the surface. In opposite, Zonterra 600, like all Zonterra GPR systems, are poor sensors. They are just GPRs without internal data recorder, without GNSS, without anything. Zonterra GPRs have power connector and Ethernet connector. And they require external data recorder. In our integrated system, we supply onboard computer for the drones, which acts as data recorder, data logger, and also it gives us possibility for the full integration between SkyHub, between GPR, data logging, SkyHub, and data from drone avionics. I mean, first of all, precise geotagging. When you use MALÅ GeoDrone deployed on the drone, you will not see real-time data feedback from the drone over any big distances. Actually, MALÅ GeoDrone has Wi-Fi access point, and from 10-20 meters, maybe 30 meters maximum, you can connect to that Wi-Fi hotspot and see data from GPR in real time. But in majority of surveys, distance will be much more larger, and you will be able to check the data only when drone will be landed and you will download the data. In case of fully integrated zone GPR systems, during all the flight, you will see current trace, or you can see profile of the data which comes from GPR to SkyHub. I should say that that real-time data is not for real-time data interpretation or for the making decision what we have on the ground. It is just to provide real-time feedback for the system operator that system is working, it provides the data, it records the data, just to have a better confidence in results during the flight. Also, quite important difference between GeoDrone and Zonterra, that Zonterra has standard options for terrestrial surveys, because again, most of GPR applications now and in future will be from card, not from the drone. So here are two bigger images of GPR, of both GPRs. For MALÅ, here is a small compartment for the battery. You can use MALÅ GeoDrone with external power source. We can provide cable to feed power from the drone to GPR. That will reduce the weight for the, so remember, 150 or 200 grams or something like that. And here is antenna of Wi-Fi hotspot and antenna for GNSS receiver. For the antenna, GNSS antenna, not for receiver. It is very important. GNSS receiver is inside of casing, and that receiver is not RTK capable. So if you need precise coordinates in your data, you need to have precise flight track or survey track and geotag the data after the flight using only timestamps in the data. Timestamps which will be recorded from internal GNSS receiver. If you don't need precise coordinates in survey results, you can use just external antenna. And you can notice that very high quality casing of MALÅ GeoDrone, and it provides really quite good protection for the hard landing or not good handling. In opposite, Zone TRX 600 doesn't have anything except GPR inside, except antenna and antenna controller. It has power connector and Ethernet interface, and even outer casing is almost missed here. So that upper part of GPR, it is very thin metallic shielding for the electronics and antenna without any external cover. Is it good? I think yes, because practice of with the previous models says that GPR is well protected by drone legs, actually, in case of hard landings. And that design provides savings of 1 kilogram of the weight. And it is important for the not big drones like DJI M400 or M350. And also, Zontaira GPR has a connector for odometer on the card. It's also important for the traditional way of GPR use. A bit more about terrestrial surveys. Zontaira 600 comes with as a standard in transportation box, but that box also has built-in battery and Wi-Fi router. So for terrestrial survey, minimalistic kit is just a transportation box. We need to put GPR inside of it, connect two cables, Ethernet and power, turn it on, close the lid, and you can drag it using crawl over the surface. For the data recording, you can use any Windows tablet computer or Windows laptop with Prism 2 software, which also comes in a kit. As additional option, Radar Systems manufactures a foldable card. The same box can be placed here, and the system can be used in a very, very traditional way, with odometer or with GNSS receiver. For MALÅ GeoDrone, at the moment, at least, they don't provide any options to support terrestrial surveys, but as we had to collect kind of baseline data, baseline for GPR means from the surface or almost from the surface, we used MALÅ GeoDrone with card from Zontaira, and it fits here almost perfectly. So that's also option. You can buy MALÅ GeoDrone and card from Zontaira. but you can improvise something like use baby stroller. It will also work. In one of my business trips, I used baby stroller to deploy to use GPR on the surface. Comparison with other models. For zoned Aero product lines, radar systems manufacturers, and we integrated with drones and supply range of GPRs which cover almost all possible airborne GPRs. Low frequency GPRs with unshielded antennas. Antennas are interchangeable. You can change dipoles in the field, and dipoles are very cheap actually. It's aluminum tubes. We tested that GPR system with frequency ranges from 50 and up to 400 megahertz, and it is lightweight GPR on the market. And it is our maybe most popular GPR system because with low frequency, usually quality of the data collected from the drone is better than collected from the surface. Because for low frequency antennas, elevation of antenna over the surface is not so significant factor as for high frequency GPRs. Next is GPR system is Zoned Aero 500. It is the only system which is certified in United States and Canada by FCC and Industry of Canada. That's the only existing GPR system on the market which can be legally used in United States and Canada without special permissions or exceptions. Next model is 600. In terms of data and application scenarios, actually, it is almost the same as 500. And it delivers more or less the same data, more or less the same penetration, because difference in central frequency, which defines all major parameters, real parameters of GPR, is not too big. Why 600, Zoned Aero 600 was introduced? Answer is very simple. To have model which is the same, has the same application scenarios as 500 megahertz system, but can be used with new drones or with smaller drones. So it's 600, and Zoned Aero 1000, 1 gigahertz system is for the specific scenarios like snow, ice profiling, and over the very dry surfaces with very low conductivity. It also can be used, of course. For MALÅ GeoDrone current line, so new model MALÅ GeoDrone 600 in terms of capabilities and all major parameters is the same as Zoned Aero 600, and they have a quite old model of low frequency radar called GeoDrone 80. It is, as I remember, 6 or 7 years old model. It is not very popular at the moment because it requires a quite big and heavy drone. Minimum is something like Grandpa DJI M600, and actually better to have a bigger drone. So more details about possible applications, expected parameters, and so on, you can find by the link. Again, you will receive a copy of presentation. So here you can find more information about each model and also something what you can expect from particular GPR system, and again it is defined by central frequency of the radar. This is my presentation. It's here. So, application scenarios for 600 MHz. It is any type of shallow profiling, shallow scanning up to 1.5 or 2 meters in average normal conditions. Average normal soil means dry soil with low conductivity. It can be sandy mix, it can be just dry soil. So in such conditions, you can get a penetration up to a couple of meters from flight altitude, about half of meter or maybe maximum 1 meter above surface. In case of snow and ice, you can fly higher, but anyway, 600 megahertz radar requires very low elevation of antenna over the surface to get useful results. So again, airborne GPRs, especially high frequency airborne GPR systems, are for large unobstructed areas with low vegetation. So main scenarios are utility search or underground infrastructure mapping. They can be used for archaeology, but very important not to detect small artifacts, mostly to detect something big like hidden basements of the buildings, or just to profile stratus or soil layers before excavation. For shallow, they can be used for geotechnical survey. Actually, technically it is the same, soil layers profiling, and they that systems are very good for not very thick snow and ice profiling. Not very thick, I means not dozens of meters. If you need to profile glaciers, you need lower frequencies, meaning Aero LF or MALÅ GeoDrone 80. Very important. All GPR systems in our portfolio are not suitable, absolutely not suitable for landmines and UXO detection. If you want to know why, we can provide you very detailed report, which we prepared using results of testing of GPR systems in controlled, very ideal conditions over test range with many different UXO and landmines. GPRs, and actually not only airborne GPRs, but also terrestrial GPRs on a card, will have so high false positive rate that they became absolutely useless. For every real target, we had dozens of false anomalies from natural objects like cobbles, stones, just pieces of the soil with different permittivity. That makes GPRs practically useless as a search tool, but they can be used as additional sensor to collect more information about targets detected by magnetometer or electromagnetic impulse detectors. But as search tools, they are absolutely useless. And just a couple of minutes about M600 integration. It is quite a hot topic because new DJI drone is just excellent, I should say. We are at final stages of integration. That's the photo what I made yesterday evening in our office. We are finalizing software part. All our GPR models will work with new DJI drone in the same way as we implemented for M300, M350. For Zonterra, we will support or deliver power, of course. We will provide true terrain following capability with external altimeter. Of course, geotagging, including high precision coordinates if drone is in RTK mode. We will provide full control from the ground station. Operator will see real-time traces or profiles. And we added in actually in the previous release of our software, but it will be also supported for M400. We provide automatic cut-off of GPR transmitter above the set altitude. It is quite important if you want to be fully compliant with the requirements of regulators. In most countries, including all European Union, including United States, including Canada, it is prohibited to carry active working GPR antenna with the elevation more than 1 meter above the surface. So drone can fly higher, for example, when it is flying to or from the survey area, but at that parts of flight, GPR should not emit anything to be fully compliant with regulations. For MALÅ GeoDrone, as it is self-contained sensor, we can provide optionally power to save the weight and not to care about one more additional battery set in the field, and we provide true terrain following capability. Yeah, and also we can provide better mountings than you can get from MALÅ because our opinion that our mountings for MALÅ GeoDrone are better, and actually you will spend our mountings don't block gimbal mounting of the DJI drones, and you will just spend much less time to mount GPR on the drone. For previous models, M300, M350, and also for DJI M400. Even if you will be not our direct customer, if you will order MALÅ GeoDrone from MALÅ or MALÅ reseller directly, you can drop us a message and we will provide 3D models of the mountings for free. That's all. We have 15 minutes for the questions. One, what software did you use for 3D representation of the GPR deliverable? We used Geolytics. I can put link in chat. We are not reseller of Geolytics. We are just friends. So if you will need Geolytics, you need to reach them directly. Next question is, we already have Zonta Aero LF. Can the GPR now connect to the DJI M400? Are the mountings and smart cables available to DJI M400? So after 2 weeks, approximately, after 2 weeks, we will start deliveries. You will need absolutely different mountings, and you will need new smart cable. Unfortunately, DJI changed everything. I mean, geometry of the drone, legs now are not parallel of the drone, legs of the drone, and they require encryption chip at the side of external computer. So yes, you need to use you will need to use smart cables. So you can get a quote right now, but delivery can be in December. Next question is, are your GPRs compatible with Matrix 400? Already answered, yes. Wait 2 weeks and you can order the kit or get the kit for Matrix 400. Next question from Sven. A client has asked us to perform moisture content characterization using drone-based GPR from surface down to 10 meters. Is it theoretically possible to derive 3D moisture content from GPR data? Do you know of any practical application? I saw some papers around that topic. Most of the papers are about soil moisture content in the top layer, because here amplitude of the reflection will be proportional, not directly, but proportional to the water content. For the 3D, actually, I don't know how that may work if you don't have known reflector at known depth. But maybe it's possible, I don't know. Question from Stefan. Can GPR be used to measure the depth of riverbed? Yes, it can be used for the bathymetry, or with some restrictions for the sub-bottom profiling, to see sediments layer and what is in sediments. But GPRs will have a quite limited maximum depth. Usually it is meters. And of course it is not for high frequency GPRs. I started to work actually article in LinkedIn. I will post a link to the draft of my article. It is in LinkedIn because it is draft, and LinkedIn is very convenient to write drafts of the articles. At some moment it will be moved to our corporate site, but you can read it, and there are many aspects of bathymetry using GPR, not only on a drone, but from the boat as well. Main limiting factors here are conductivity of the water. It should be very low conductivity, and maximum depth. But in some cases you can easily collect very good data. For example, here is bottom profile from Thorn River in Sweden. Water has extremely low conductivity. In some parts we see sub-bottom structure, like here. So here you can find useful information. Next is, does the LiDAR on top of M400 replace the radar on top from M350 for obstacles avoidance? Yes and no. First of all, at the moment we didn't find a good way how to install a radar obstacle detector, I mean what we supply for M400. LiDAR of M400 may fail in some environmental conditions like fog or heavy rain. Anyway, it is much better than nothing. At the moment, in the current system and software release, we will not support our radar sensor for the obstacles, but maybe we will support it in future. Next question, what maximum altitude of drone we can fly? It's dozens of centimeters for high frequency radars like 1 gigahertz or 500 megahertz systems. It's maximum few meters for low frequency systems. So again, drone-borne GPR applications are for large areas without high vegetation and without obstacles. In some situations, you can collect good data flying higher. For example, we have data examples for the very good examples for glaciers. With low frequency antenna, you can fly at 10 meters, 5-10 meters above the ice and still have a penetration till dozens or even hundreds meters into the ice. Or you can, in case of very dry sand, you can have a penetration of few meters for 600 or 500 megahertz systems. But if you are in Europe, for example, or in the most of United States and Canada, you need to fly very low to collect useful data. So more information you can find, and as well as recommended flight altitude, you can find by the link. Next question from Michal. According to your experience, what is the prospection depth range for the survey with 600 megahertz or freshwater reservoir? I suspect that in most cases, it will be something between 0 and half of meter from drone. I saw a bit deeper, but flights were too extreme even for me. So sensor to water clearance was around 20 centimeters. For me, it is too low. Better to use both, or better to use a sounder or low frequency system. Main factor here will be as for all bathymetric applications, conductivity of water and your readiness to fly very low, having insurance, of course. Next question from Duke concerned about using GPR with drone for detecting groundwater up to 100 meters. Any ideas? No ideas, and it is practically not possible. So standard tools for the groundwater search are transient electromagnetics with big coils or ground surveys like conductivity, resistivity surveys, but not GPR on a drone. Next question is from Benjamin. Hello, what is low flight recommended for 600 megahertz? Actually, I already answered it. By the last link in chat, you can find a lot of information about different GPR systems. So ideally for 600 megahertz, you should fly not higher than half of meter. And data examples, what I demonstrated, were collected with the antenna to ground elevation half of meter. From 1 meter over the road or over the dry surface, you will still get useful data. Higher, most probably only in very good conditions for GPR, meaning very dry sand, snow and ice. Over the normal soils, it should be very low. Question from Stefan. Do you absolutely need to use UgCS flight software to plan GPR drone missions? Yes, because you need terrain following. DJI standard software doesn't support terrain following. To be fully correct, DJI M400 has terrain following capability with some entry-level altimeter, but it doesn't work over snow, over ice. DJI doesn't recommend to use it over surfaces like water, and it doesn't work at very low altitude. So answer is yes, you need UgCS. Guido, it's pity that you forgot which of the shown sections was from GeoDrone of RadSys's. From publications, I assumed that lower section was from GeoDrone because it had a much better wavelength. Would you comment on that? I don't want to start discussion what data is better because again, it was collected in different conditions. So we can discuss difference in the data when we will collect the data at the same day. It's a very short time between surveys with absolutely the same survey parameters. For me, the quality of the data is the same and they both work good in that regards. If you want, I can share raw data. You can just drop me a message and I will show you. I will share with you data. Next question from Niels. I'm working for a mining company, dewatering Dolomites. As a result, exposed cavities at TC within the Dolomites. Therefore, looking for the option for geotechnical work. The depth of the weak zones would be between 20 up to 60 meters. What would the penetration depth of that system? So in theory, you can achieve 20 plus meters using low frequency GPRs. I mean on Aero LF with something like 75 megahertz antennas. If water content is really very low, in theory. Deepest what I saw from the drone was around maybe 20-30 meters and very dry in the middle of desert actually. Maybe that will work in Dolomites as well. Also from Niels, also looking at water ingress that could cause sinkholes to form sinkholes and so on. It's pretty standard application for GPRs with low frequency GPR with penetration limits, of course, you can do such surveys. Question from Matya. Which GPR is then more suitable for landmines? No one GPR is suitable for landmine search. No one. We tested 1 gigahertz. We tested 150 gigahertz. So extremely high false positive rate, even in ideal controlled conditions. Ideal controlled conditions, I mean test range with replaced natural soil with the clean sandy mix gives extremely high false positive rate. It doesn't depend on what brand you will use. 3D radar, MALÅ, radar systems, GSSI, sensors and software. You will get absolutely the same. No one. Question from Kim. Which sensor would you recommend to use for surveying large area of land to look for potential areas where flooding could take place? Kim, I'm very sorry, I didn't get the question. Usually to analyze the potentially flooded areas, you need to collect elevation data, not GPR. Or I don't understand that application. So actually, you can drop me a message and we can discuss that in details. If it is about kind of geotechnical surveys, for geotechnical surveys, you can use low frequency GPRs because in general, penetration of high frequency models like 500, 600, especially from the drones, will not be enough. And last question is, can you share me a recommendation to monitoring pipeline? I need to check fuel lines and leaks. So leaks detection from using GPR is extremely complicated task. I can recommend a couple of videos, not ours actually. Give me a moment, I will find the link. It's a GPR published by Bigman Geophysics. It's I would recommend their channel. I learned a lot from it. Check that video and you will better understand. Yeah, maybe it is the same video. It is extremely complicated task, not for the drone-mounted GPR, but also for terrestrial surveys. More or less, it will work over the uniform soils, not very saturated, to see in the data areas with increased dialectical permittivity. From the drone, usually it will not work, and yeah, it is very bad, not predictable scenario. Just to find pipes, you can use practically any of GPR systems, but yeah, you need to select right central frequency according to the diameter, depth of the pipe, and conditions of the soil. But leaks detection, it is unpredictable task. It seems that's all.